Okay, let's look at an example where we have a vector field as shown and a parameterization for a path, and we want to find the line integral along that path in that vector field. So what I'm going to do first of all is to check whether that vector field is conservative. Because if it is, then the fundamental theorem of line integrals is usually an easier way of calculating things. So remember, we were going to compare the partial of the first component with respect to y to the partial of the second component with respect to x. Partial of the first one with respect to y comes out to just be 2x e to the y. And the partial of q with respect to x is also 2x e to the y. So yes, it is indeed a conservative vector field. So that was our first step. Now we're going to find the function little f. So what I know is that capital F is the gradient of little f, which means that the first component must be the partial of f with respect to x, and that the second component is the partial of f with respect to y. So in other words, I want for the partial of f with respect to x to be 4 plus 2x e to the y, whereas the partial with respect to y should be x squared e to the y plus 2y. I'll take the first equation and integrate both sides with respect to x. So then I get that f must be equal to 4x plus x squared e to the y. Maybe let me just annotate this. I'm integrating dx here. And then after I integrate everything that's sitting there, I have some constant function of y that I'm not sure what it is. So okay, I know that some function little f exists, and it must have this general form here. And now you can do one of two things. Either you can take the derivative of f and compare to this, take its derivative with respect to y and compare to this, or you can integrate this with respect to y and then kind of compare those two. And you know, there's no particular reason to prefer one over the other necessarily. The benefit of, say, differentiating f with respect to y is that taking derivatives tends to be easier than taking integrals. But if your function is kind of straightforward enough, then it's not too hard to go ahead and just integrate both. So let me just do it that way. If I integrate this with respect to y, we find that f has to be x squared e to the y plus y squared plus some function of x. And now you say, okay, well, I want f to be written in both of these forms, and you kind of just take all of the terms that appear in at least one of these, but make sure you don't duplicate the terms that appear in both. So if I take f to be 4x plus x squared e to the y plus y squared, well, then it looks like the first form because it's 4x plus x squared e to the y plus a function of y, and it looks like the second one, which is x squared e to the y plus y squared plus a function of x. But actually at this stage, the easiest thing to do is to just compute the gradient and to just verify that the gradient really is the vector field that you started with, and it is in this case. Okay, so I have my little f, so now what's the point? Well, now we're going to use the fundamental theorem of line integrals, which says that if what you're interested in is this line integral, you can just take little f of the end point minus little f of the start point. Right? And this happened exactly because capital F was the gradient of little f. Okay, well, I need to know what the end point and the start point are then. So we go back to look at our parameterization. The path is given by this r of t over this range of t values. So the start is r of 1, which is the point 1, 2. And the end is r of 2, which is the point 2, 5. So I want f of 2, 5 minus f of 1, 2. Okay, now we just plug that into this function that we found here for little f. So that looks like 8 plus 4e to the 5th plus 25 minus 4 plus e squared plus 4. And okay, there's some simplifying we can do there, but at that point it's straightforward enough.